All right, so let's say I have a function f, and let's say the function f, we are going to use df to denote the domain of that function, and then rf will denote Alright, so this is what I mean. Let's say I have a function f, and the function f has domain df and the range rf, okay? And we are going to assume that f is one-to-one, okay? So it's a one-to-one function, and once again, what that means is that if I write down the domain of f in one column, let's say the domain values are x1, x2, x3, x4, dot dot dot, and let's say I have the corresponding range values, so let's denote them by y1, y2, y3, y4, dot dot dot. So let's say the first column contains all the distinct input values, and second column contains all the distinct range values. So the first column doesn't have the same number twice, okay? The second column does not have the same number twice, okay? Now, if f is not one-to-one, then there's got to be at least one range value. There's got to be at least one range value for which we have two arrows going to that. That is, maybe x2 is assigned to that, and maybe something else is assigned to that. If f is not one-to-one, then there's got to be one range value associated with at least two distinct domain values. But we are assuming that f is one-to-one, so that means that I can think of this function as this. So that there is a one-to-one correspondence between the domain and the range. Now, if I have a function which is one-to-one correspondence, then I can look at the corresponding reverse function, which is we are going to take the basically now we take the domain to be the range of f. So I have y1, y2, y3, y4, dot dot dot, and then I have the inverse function evaluated at y would be the corresponding value in the domain of f. Okay, so here the function is y1 is assigned to x1, y2 is assigned to x2, y3 is assigned to x3, y4 is assigned to x4. Am I making sense? So what the f inverse basically is doing the opposite of f. We are basically reversing the assignments, right? If I view the function f as an assignment, it takes x1 to y1, x2 to y2. It takes x3 to y3. If I view the function f as a set of assignments, then the inverse function is basically reversing the assignments, right? Okay, so that's the inverse function. And how did we write down the domain, the definition of that inverse function? So altogether here, I'm assuming f is one-to-one. So still f is 1 to 1. So okay, let me write that down again. Given that f is 1 to 1, and I am thinking of f having domain df and range rf, okay, then we define a new function which we are going to use the symbol f to the negative 1 to denote that new function, and that new function will have domain equal to the range of f, and it will have range equal to the domain of f, by saying that f inverse evaluated at some number a will be equal to b if and only if f of b is equal to a. Okay. So remember, in the above tables, that's what we did. We reversed. So if f takes b to a, then f inverse takes a back to b. In other words, here is my a and here is my b, and f takes b to a, then f inverse is taking a back to b, right? They are doing opposite of each other. So that's how we defined the inverse of f. Of course, given that f is 1 to 1, otherwise you cannot define this function. Now, how do I know that? So what did I do? I've given the function f, which is 1 to 1, I defined a new function. But let's try to justify why this is a valid function. Now, what's the condition for a input-output process to be a valid function? The condition is that every input value leads us to exactly one output value, right? So let's just think about why f inverse is a valid function for a second. So if I have, let's say, a input value a for f inverse, and let's say f inverse takes a to some number b1, and it also takes a to some number b2. So let's say I have f inverse taking a to b1, and also f inverse takes a to b2. Okay? Can that happen? If that happens, if b1 and b2 are distinct, right? If b1 and b2 are distinct, and if this happens, then f inverse is not a function. But notice that what happens, the way we defined f inverse of a is b1 simply means what? Simply means f takes b1 to a. And then, because f inverse of a is b2, I can say that f takes b2 to a as well. So what is happening? F is taking, if f inverse takes a to b1 and b2, then f must take b1 and b2 to the same a. Right? However, that can't happen, right? If b1 and b2 are distinct, that cannot happen because f is 1 to 1, right? For f, two distinct inputs cannot go to the same output, right? So that justifies that f inverse is indeed a valid function. It cannot take one input to two distinct outputs. Because if it does, that would mean that f takes two distinct inputs to the same output. Right? So f inverse is indeed a valid function. Can't happen. This can't happen. Well, let me say differently. b1 has to be b2 since f is 1 to 1. So which means that indeed f inverse takes each input to a unique output. So this is a valid function. Let's look at an example. Let's say I have the function f of x, and the function f of x is given by x plus root x. What you have to find is the value of the inverse of f at 6. So what's the value of the inverse of f at 6? Let me give you 30 seconds to think about what the answer is. What is f inverse of 6? Go ahead. No. Very good. Why is that? Yeah. So the answer is indeed 4. Very good. So this is the explanation for this. And notice that let's say f inverse of 6. So let's say f inverse of 6 is some number a. Okay. We are trying to find a. Well, what would that mean? It means that f inverse is taking 6 to a. But then f will take a to 6. So in order to find f inverse of 6, I basically have to find a number a such that f of a is 6, right? I have to find a number a for which f of a is 6. Which means I have to find a value of x for which f of x is 6, right? Well, by just looking at my function, I can see that f of 4, just by inspection, f of 4 is 4 plus root of 4, which is 6. So because f of 4 is 6, clearly then f inverse of 6 would be 4. Right? So what is f inverse of 6? F inverse of 6 is a value of x for which f of x is 6, right? F inverse of 6 is a value of x for which f of x is 6. Okay? Let's do one more example like this. Let's say I have h of x, which is 2x cubed plus 3x squared plus 7x plus a 4. And what I have to find in this case is h inverse of 4. So what's h inverse of 4? So once again, h inverse of 4 is a value of x for which h of x is 4. 0. Very good. So notice that by inspection we see that so basically you're trying to do the following. Okay, you're trying to solve h of x equals to 4. Okay, you're trying to solve that. You're trying to find the value of x for which h is 4. Well, it's clear that h of 0 is 4. Again, this is by inspection. H of 0 is 4. So then I can say that h inverse of 4 is 0. Is everybody okay with it? This is we are going to use this trick in other problems later. Any questions on that exercise? Maybe one more. Okay, so one more. let's say I have g of x, and that's equal to x plus cosine x, and I want to know what is g inverse of 1. Can you tell me what g inverse of 1 is? What's that? 1? 0. The g inverse of 1 is 0 because why? G of 0 is what? G of 0 is 1, so this would be 0. Since g of 0 is 1, right? It's 0. G of 0 would be 0 plus cosine 0, right? And 0 plus cosine 0 is 1. This is 0 plus cosine 0, right? Cosine 0 is 1. So g inverse of 1 would be 0. Is that okay? Everybody's okay? Okay, so let's look at how f and f inverse interact with each other when we take the composition of the two. So let's say, once again, before I go on, I want to write down the terminology. Sometimes we say that f is invertible if the inverse of f is defined. What I mean to say here is that basically f is invertible if f is what? 1 to 1, right? If f is 1 to 1, f has an inverse, and that's when we say that f is invertible. If f is not 1 to 1, then it's not invertible. All right, so this is just to introduce you to the word invertible, okay? So let's say I have an invertible function. It means that f inverse exists. Now, my question to you is that if I take the composition of f inverse and f, what am I going to get? Now, when I take the composition of f inverse and f, where should x come from? X, the input x for the composition, right? Where should x come from? Should it come from the domain of f or from the range of f? Domain of f, because you are applying, what function are you applying first? F. Now f of x is defined only if x is in the domain of f, right? So x has to be in the domain of f. Okay. On the other hand, can you also tell me what is f of f inverse of x? And in this case, x has to be where? Well, x has to be in the domain of f inverse now, right? But the domain of f inverse is what? The domain of f inverse is the same as what? The range of f, right? The range of f. Okay. Someone please tell me what is the value of the left-hand side in both cases. What is f inverse of f of x? What's that? Well, let me make it a little bit easier for you. Let's say I have x, right? And I have f of x. So x is assigned to f of x by what function? The function f takes x to the value f of x, right? So in the first case, in the first composition, now you're applying f inverse, right? So f inverse, it's going to come back to x, right? So now if I apply f inverse, I just go back to x, right? So that means this is exactly x, right? f inverse of f of x, right? Whatever f of x is, f is taking x to something f of x, and then f inverse applied to that will just take it back to x, right? Remember, they are doing the opposite of each other. So whatever f does to x, f inverse will basically do the opposite, right? And can you tell me what's the second one? It's going to be x as well, right? Is everybody okay? Both of them are in fact x. Alright, so in the second case, basically what I should be saying then is let's say f inverse takes x to f inverse of x, and then when you apply f, you go back to x again. Okay. All right. So these two are very important properties of inverse functions. In fact, the function f inverse, the inverse of f is completely determined by these two properties. What do I mean by that? When I say that the function f inverse is completely determined by these two properties, what I mean is that if you give me another function g and you tell me that that function g satisfies these two properties with f, then that function g has to be f inverse. Okay? So let's say you have a function f. So let me say it this way. Let f be a function let f be 1-to-1, so it has an inverse. If let me see how I want to say it. The function g satisfies f of g of x equals to x, and g of f of x is equal to x. This is for all x in the domain of g. This is for all x in the domain of f. If the composition of f and g in any order is equal to x, if and only if g is the inverse of f. Okay. So if you have any function g such that the composition of g with f in any order is just the identity function x, okay, then you know that g has to be the inverse of f. Okay, that's what I mean, that f inverse is completely determined by those two properties. Okay, is everybody clear what I said? Okay. Here's an example. Okay, so suppose that I give you a function f which is x to the 3, and let's say I give you another not x to the 3, let's say x to the 5, and I give you another function g of x which is x to the 1/5, and I ask you decide if f and g are inverses of each other. Okay? Decide if they are inverses of each other, meaning that decide whether g is the inverse of f, or decide if f is the inverse of g. Okay? How would you do that? Well, all you have to do is check the two cancellation properties that I gave you. What is f of g of x? The properties that I gave you above, these are called the cancellation properties for inverses. So this is f of g of x is x. Sorry, f of g of x is equal to f of x to the 1/5. And then what is f of x to the 1/5? Well, x to the 1/5 to the power 5, that's the value of f when you apply f, and that's exactly x, right? And then when you apply g of f of x, you basically get g of x to the 5, which is x to the 5 to the 1/5, because the function g is basically taking the fifth root of the input, so I get x back again. So we see that f and g, the composition of f and g in any order is the identity function x. So that implies that f and g are inverses of each other. So g has to be the inverse of f. I could also say that f is the inverse of g. Good point. Yeah.
You always get x out of it, or do you get x squared?
All it has to be x. For f and g to be inverses, the composition has to be x. All right. So let me see. Let me do another example on finding given a formula for the function f, find the formula for the inverse function. So let's say I have a function g of x, and let's say the function g of x is the root of 5 minus x. Okay, and the question is, what is the inverse function g, or what is g inverse of x? Let's say. Okay, that is, I'm trying to find a formula for g inverse. So how would I do it? Well, we are going to let y to denote g of x, right? So y denotes the output for the input x under g. So then I know that y would be the root of 5 minus x. Okay, and then what I'm going to do is say, so y is the output, x is the input for the function g. Now the inverse of g does the opposite, right? It takes y back to x, right? So that means that all I have to do here is solve for x. So if I square both sides, I am going to get this, and then x would be 5 minus y squared. Okay, so that means that g inverse of y is 5 minus y squared, right? Because the inverse will take y to x, and the formula for x in terms of y is 5 minus y squared, right? So that's the inverse function. However, usually we don't use y for the input, right? Usually we use x for the input. So g inverse of x would be 5 minus x squared. Okay. This last step is unnecessary, but it's just tradition to use x. Usually you cannot really use x all the time as the input. Sometimes you do use y for the input for a function, but it's just I guess the tradition that you see in all textbooks, that they always express the inverse in terms of x as well. Okay, but I mean, what's the difference between what I wrote, g inverse of x and g inverse of y? They are the same formulas. Okay, so everybody's clear how to find the inverse? Okay. Let's now think about how are the graphs of f and f inverse related, okay? How are the graphs of f and f inverse related? So, first of all, let's say I have that f of a is equal to b. Well, if and only if f inverse of b is equal to a, right? You agree? In other words, if I have a and b, f is taking a to b, then f inverse is taking b back to a. Now, wouldn't that mean that, whoops. Okay, f of a is b. F of a is b. Doesn't that mean that AB lies on the graph of f? Graph of f, if and only if the point BA lies on the graph of f inverse, right? Remember, f inverse is what? It just does the opposite of f, right? So if AB is a point on the graph of f, then BA is a point on the graph of f, right? And vice versa. AB on f on the graph of f means BA would be on the graph of f inverse. But in terms of geometrically, what are the positions of the points AB and BA? So let me draw my favorite xy axis. And let's say I have the line. Let's say I have the line y equals to x right here. Whoops. Let's say I have the line. So let's say this is the line y equals to x. And if I have that this point here is AB, then what's the position of the point BA? What's the position of the point BA? The position of, so from the point AB, I'm going to make a vertical line onto the line y equals to x, and then I am going to go directly on the other side at equal distance, and this point here would be BA. In other words, okay, let me make sure this distance here and this distance here are the same, and this is a vertical angle. Okay, this is a 90-degree angle here. So what I'm trying to say that if I know the position of AB, the position of BA is determined by this. Okay? Is everybody clear? So the point BA is basically the reflection of the point AB across the line y equals to x. Yeah. Yeah, that's what we did. Yeah. We switched. We had AB. We switched to BA. Okay. So so then, if I understand that the relationship between the positions of AB and BA, then what would be the relationships? What would be the relationship between the graphs of f and f inverse? Yeah, the graph of f will be the reflection of the graph of f inverse across the line y equals to x. So let's do an example of that. Let's look at an example. Let's consider the function f of x to be the function root negative x, negative 1. Okay. What's the domain of this function? What's the domain of this function? Well, whatever inside the square root has to be non-negative. Negative x, negative 1 has to be non-negative, which means negative x would have to be larger than 1, which means x has to be less than negative 1, right? X has to be less than negative 1. So, that's the domain. And what's the graph? What's the graph? Well, you can start with the graph of root x and then apply the transformations that you have learned in Calc 1 or Pre-Calc in order to come up with the graph of root of negative x, negative 1, right? So what's the graph? Yeah. So the graph will look like this. Okay, so that's the graph of this function. Okay? And, okay, so then, what is this point here? This point here is negative 1 and 0. If the point negative 1 and 0 is on the graph of f, then what will be on the graph of f inverse? 0, 1, right? 0, negative 1. So if I reverse the coordinates, I get 0, negative 1. Let's say 0, negative 1 is right here. Whoops. That's the 0, negative 1, let's say. 0. So this is 0, negative 1. So this point here will be going this the corresponding point on the graph of f inverse will be 0, negative 1. And then how will the graph look like? Someone said shooting, what was that? Shooting star going upward. Well, now we're going to have something like this. Shooting downward, I guess. Okay, and well, I forgot to draw the line y equals to x here. So across the line y equals to x, they are reflections of each other. Okay, this is y equals to x. This is f inverse. This is f. Okay. And just to emphasize, if I have a point here, if this point here is the point AB, then this point here is the point BA. Okay? Is that making sense? Is everybody okay? Everybody's okay? All right. So remember, I did a couple of examples with the trig functions. We had the sine function, and the sine function we restricted the domain to negative pi over 2 to positive pi over 2 to make it 1-to-1. If it is 1-to-1 there, then it has an inverse. Why don't you try to come up with the graph of the inverse sine function, okay, on your own when you go home today. And also do the same thing for cosine and tangent, and see if you can come up with the graphs of the inverse trig functions. We are going to discuss those pretty soon, and if you do that exercise, it will come easier for you. All right, so that's how we can find the graph of the inverse function. Any questions on that? Okay, so there's one more thing that I have to do here, which is we have the new function f inverse. Given a 1-to-1 function f, I have f inverse. Now, it is natural to doubt that the derivative of f inverse can be found from the derivative of f, right? So how can I find the derivative of f inverse from the derivative of f. So in order to, before I answer that, let me just write down a fact. And that fact is if f is 1-to-1 and continuous on an interval I, then f inverse is continuous on the interval J, which is basically the output values corresponding to I. So when I write that, I mean that under f, you look at all the output values of the elements of I. That's going to be an interval, and f inverse is continuous there. The continuity of f inverse should not be. So basically, what this is saying is that if f is continuous, f inverse is continuous, which is clear because if you think about the continuity in terms of the graph of f, if the graph of f is nice, then the graph of f inverse has to be nice, right? Because it is just reflecting across the line y equals to x. So this should be intuitively clear that if f is continuous, f inverse should be continuous as well. Is everybody okay? If you want to think about how to prove something like this in a rigorous way, you can. It's not hard, but I won't do it. Here's my theorem to find the derivative of f inverse. This is what you have to remember to do some of the homework problems. If f is 1-to-1, again I'm saying 1-to-1 again and again to say that f has an inverse. If f is a 1-to-1 differentiable function, and if the derivative of f evaluated at f inverse of some number alpha is not 0, then f inverse is differentiable at alpha. And what's the derivative of the inverse? So I'm going to write f inverse prime for the derivative of f inverse. What's the derivative of f inverse at alpha? Well, it is given by 1 over the derivative of f evaluated at, and this might look strange, but f inverse of alpha. So basically the derivative of f inverse is 1 over f prime, right? Almost what we have is that the derivative of f inverse is 1 over the derivative of f. Okay, stare at this formula, and you see the why we needed the condition that the derivative of f does not vanish at f inverse of alpha, because otherwise you're going to have the denominator is 0. Okay, so that's the formula for the derivative of f inverse in terms of the derivative of f. One thing I want to emphasize here when we look at this formula here, this thing here is really should make sense. Why? See, alpha is in the domain of f inverse. Alpha is not, it may not be in the domain of f prime. So here is alpha, and it is in the domain of f inverse, and here is f inverse of alpha, and let's call that beta. So we have that f inverse takes alpha to beta. Well, then you know that f of beta, f takes beta to alpha, right? So what we are saying is that the inverse function, the derivative of the inverse function at alpha is the same as 1 over the derivative of the function f at beta, right? This is what we are saying. Where beta is the image of alpha under f inverse. Beta is the output value of alpha under f inverse, right? That's what we are saying. Am I making sense? You have to memorize this formula for the next exam. Okay. All right. So let's do an example, and would you guys give me maybe a minute to do just one example? Okay, just to make sure that this explanation is complete. I have, let's say, the function f of x, which is 2x plus cosine x. And let's say what I want to find, it is the derivative of the inverse at the number 1. I want to find the derivative of the inverse at the number 1. Well, the formula that I just gave you, it tells me it's the same as 1 divided by the derivative of f evaluated at f inverse of 1. Now, what is f inverse of 1? F inverse of 1 is the value of x for which f of x is 1. Right? Can you give me a value of x for which f of x is 1? 0, right? We did an example like that a few minutes ago. So I know that this is equal to 1 over f prime of 0, okay? Again, what we are saying here is that f of 0 is 1, okay? F of 0 is 1, or f inverse of 1 is 0, right? So the derivative of the derivative of f inverse at 1 is the same as the derivative of f at 0. Oh, sorry, 1 over that. And then what is 1 over f prime of 0? Well, what is f prime of x? 2 minus sine x. That's the derivative of f. So then we know that this is equal to 1 over 2 minus sine 0, which is half. Is everybody okay with that? All right. We are done with section 6.1. I am going to do a few more examples tomorrow before I start section 6.2 star. In your text, there is a section 6.2. There is a section 6.2 star. We are going to 6.2 star. Okay.